Okay, so we can start. And in the last class, what we have seen this important lemma, which will be there with us as long as we are analyzing randomized algorithms. Okay, this lemma is in a nutshell, what we have got is that a big experiment, say we are flipping 10 coins simultaneously. Okay, that big experiment, we are decomposing it into chunks. That means we are decomposing it into simpler experiments. Okay, and then each of these simpler experiment we are analyzing with indicator random variable. Okay, and then with the linearity of expectation, we are summing it up and then we are processing it. Okay, so that is in a nutshell what we are trying to do in an ad hoc fashion, time after time. Okay, so this thing we'll be doing time after time, and the indicator random variable, that simpler experiment we can cover up. That means that simpler experiment will be having two answer, perhaps, if we are associating some events to it. So from that sample space, if we are associating some event, then we are saying that it is becoming the yes no type of answer. Okay, whether the head is coming up or not, whether the ith interview, whenever it is happening, whether that candidate will be hired or not. Okay, whether food will be served on a particular day in your hostel or not. Okay, right. So all these things will be coming into picture. That means this simpler experiment will be boiling down to answering yes no question. And based on that, if it is yes, we are counting that it is happening once. If it is zero, we are counting that it is happening 0 times. And that is the basic fundamental idea. And whenever we are doing that, so the indicator random variable, its expectation, x is the indicator random variable associated with some event A. Okay, I can denote the random variable, indicator random variable, by this or by this, if the context is clear that this is indicator random variable associated with this event A. Okay, this is little bit annoying notation, indicator random variable, but more interpretive. Okay, right. Anyway, so that expectation of x is boiling down to probability of that event associated with indicator random variable is happening. So this is the lemma that will be coming time after time in our analysis. Okay, so this I call this lemma 1. Try to remember this lemma 1. Whenever I will be telling by lemma 1, you should be associating this, that this is related to expectation to probability mapping. Okay, it is by default, that means by definition you are getting this proof. Okay, and we have seen that, okay, this if it is indicator random variable, by definition, if it is happening, that means indicator random variable having two values, one with that probability A and 0 with that probability A bar. That means its complement. Okay, that means it is not happening, right? Not happening, we are counting it as 0, the indicator random variable value. If it is happening, we are counting it is 1 times the probability of A. So this is the definition of the expectation. And if we are putting that definition, we are getting 0 times that probability A bar, that will be 0. And 1 times probability A, that will be probability A. So expectation of the indicator random variable. This is not true for general random variable. This is true for indicator random variable. expectation of x is equal to the probability of the event associated with that indicator random variable. Okay. So this lemma will be coming into picture many times. So that's why I had a little more discussion on it. Okay. So this one example one more example, we have seen that, okay, whenever we are flipping two coins simultaneously, we can decompose it into simpler experiment and we can find out its expectation with that by summing up all these simpler experiments. Okay, that we have seen, that example. It is one more example and more general, that if we are flipping n number of coins, then what will happen? What will be the expected number of heads? Expected number of heads. Okay. So this x is the total number of heads we are trying to count whenever we are flipping n number of coins. Okay. And intuitively, this expectation of x might be coming in by 2. That is, if n is, that is the number of coins we are flipping n equal to 100 times, expectation of x will be coming 50 times. Okay, that means on an expectation we are having 50 coins coming up heads. Okay, right. So this thing will be solving by using indicator random variable. The first approach is that, okay, we can think that this is a single big experiment, thousand flips, single big experiment, and then we are putting the sample space like age up to 1000, and then age, then t, something like this. So all these sample space we have to first jot it down, and then the random variable. If we are having two flips simultaneously, we are having two flips simultaneously, then we have seen the x will be having value 0, 1, 2. If I am having 100 flips, so based on this sample space, we have to find out x equal to 0, all t's. Okay. So all t is then followed by h, so x equal to 1. So all these we have to note it down. First of all, we have to have this sample space which is absolutely cumbersome to tackle. Okay. If I am thinking 100 flips simultaneously, and then I am looking for number of heads, then as we did in two coin flips experiment, so similarly, we can do for 100 flips, but that is quite annoying. Okay. And at some point of time, you'll be thinking that, okay, this process is not a good way to deal with. Okay. Then what is the way out? The way out is this second approach, where we can think n flips happening sequentially. Okay. That means first coin I am flipping, then I am noting the result. Then second coin I am flipping, noting the result. Okay. So that means for each coin flip, we are associating a random variable xi. That means, say, for this first coin flip x1, second coin flip x2, and so on. And then we'll be summing up all these to get this x. This x will be equals to x1 plus x2 up to xn. Okay. And this x1 is nothing but a single coin flip experiment. Okay. And I am counting that. So single coin flip experiment, whether head is coming up or not, we are already in the process of utilizing indicator random variable. Okay. So that is the main idea. We are decomposing a big experiment into simpler ones, and we are taking the help of this indicator random variable and trying to solve it. So what is happening? This we are denoting this xi by this indicator random variable, that the ith flip resulting in the event h. That means head is happening. Okay. So this xi, this is the indicator random variable I associated with this event a, and this a in our coin flip experiment is that head comes up, head coming up, in ith coin flip or not. Head coming up in ith coin flip. Okay. So this is the definition. We know if it is one, if happens, zero otherwise. So this is the definition. Okay. That we know how we are defining this indicator random variable. So let x be the random variable denoting the total number of heads in n coin flips. Then x will be equal to what? This x1. It is counting whether the head coming up in the first coin flip plus this random variable counting the next coin flip, head coming up or not, or the number of heads in the next second coin flip, number of heads in first coin flip. Okay. And this is xn. So you can write that this x is nothing but summed up of xi, I equals to 1 to n. So as I told you that this form we should be utilizing. So try to think of what's happening. So first coin flip, and then I am associating indicator random variable with it, and I am counting that whether first coin flip giving head on head. Okay. Then the second coin flip also, then the third, then the fourth, and up to xn, whatever n we are having. Okay, and we are summing it up. That means for all n coin flips, how many heads we will be having, and that we are denoting by this x. Right. So you can think of, say, uh, whether you will be taking food in the hostel each day. Okay, each day. Right. So this x1 is denoting the indicator random variable associated with the event A, and this event A. Okay. So this event A is denoting that whether you will be taking food or not, or you will be taking food. Okay. So if it is you are taking food, then on that day you have counted that you have taken food once. If you take and zero otherwise. Okay. So that is the way we can define that whether you are how many times for, say, for 365 days in a year, n equal to 365, okay, you will be taking food, right? So maybe after getting this thing, that means coin flip experiment, we can try to analyze this probability, okay, and whether you will be taking food in the hostel or not. Maybe we can concentrate on this. Okay. So let us take this with n number of coin flips, how many heads coming up. So we have got this thing, x equal to the summed up of all eyes xi's, okay, for all I. So that means we have got x equal to summation xi, I equals to 1 to n. Now what we have to do is we are trying to find out the expected number of heads in n coin flips. So we are taking expectation both sides. So this expectation I am taking both sides, okay. And we have seen that, okay, if I expand this series, then it will be expectation of x1 plus x2 up to xn, okay, up to xn. So if I expand inside this bracket, whatever, x1 plus x2 up to xn. And then this is, we have seen that if expectation of x1 plus x2, then we are getting that this is nothing but expectation of x1 plus expectation of x2. If I am having three variables, I can decompose it x1 plus x2 plus x3, then expectation of x1, expectation of x2 plus x3. If I am having n variables, then this is by linearity of expectation. So we are nothing but we are having expectation of x1 plus expectation of x2 by linearity of expectation plus up to expectation of xn. Okay. So what we can do, we can write this summation. That means expectation will be inside right now. By linearity of expectation, you have to write expectation of xi. Now if I expand, then it is becoming expectation of x1 plus expectation of x2 plus up to expectation of xn. Okay. So this is by linearity of expectation. By linearity of expectation, right? And now this expectation of xi means what? This is for a single coin flip experiment, expectation of xi. Then what we got to do, we have to apply that lemma 1. Okay. Expectation of xi means the probability that ith flip resulting head. Okay. So you have to deal with that. I equals to 1 to n, this probability that ith flip result head. So A is we have defined earlier. So this expectation of xi and this probability of that event A happening. A means that ith flip resulting head. So that ith flip means it's a single coin flip. Okay, it's a single coin flip. And whatever happened earlier is not having any effect on that particular ith flip, what will be happening, whether it is head or whether it is tail. So it is absolutely independent random variable. Okay. And then so if I think that ith coin flip is a single coin flip experiment, what is the probability that head will be coming up? Half. Okay, so this half is there. So that means I equals to 1 to n, this is half. Okay. So now this I equals to 1 to n half means half plus half up to n terms. So it is n by 2. So whatever we were expecting, that is expectation of x is becoming, will be n by 2, and that is mathematically we have got this result. Okay. Right. Now if I am coming back that whether you will be taking food on a particular day or not. So for 365 days, how many days you will be taking food? Okay. Then it will be so this x is counting the number of days. That means for n number of days, how many times you will be taking your food in the hostel. And this xi, on a particular day you are taking food or not. You are taking food. Now the same expectation, taking expectation inside. Okay. Now this the result will be same, but here whenever I will be coming here, that means this A, you have to think of A in terms of coin flip experiment. A is whether head is coming up or not. Head is coming up in ith coin flip. Now for your food taking case, okay, whether you are taking food on that particular day, okay. So what will be the probability of that? Hmm? Maybe 1 by 10, 10% chance you are taking food in the hostel. What? Even less or more? Now more. Huh? So that A will be changing case to case. Otherwise, all the treatment will be same. Each big random variable to be decomposed into simpler one, and then you have to add up. You are getting whatever you are trying to achieve. Okay, by decomposing it into simpler random variables, right? And that probability, whenever the probability of that event A is coming, then it will be changing application to application. For coin flip experiment, it is half, and for your food taking case, maybe it is 1 by 10 or something else. Okay, maybe now maybe 2 by 3. You are taking regularly. You are taking food in the hostel. Okay, occasionally you are missing, maybe, right? So you can think of it as 2 by 3 or 1 by 10, whatever. Okay. So this probability of A will be changing case to case, right? Okay. Now we are coming back. We are coming back to our hiring assistant problem. Okay. We are coming back to this hiring assistant problem. We have got all those detail. That means all preliminaries we have discussed regarding probability, regarding expectation, regarding the random variables. Okay. Now we are ready to analyze our hiring assistant problem. All that knowledge we are trying to apply in our computer science field. Okay. That means that hiring assistant problem, we are developing algorithms, and how our algorithm will be performing, we are trying to analyze. Okay. Now, right. So now that n number of coin flips, whenever we are having, we are decomposing it into simpler random variable. That means per coin flip, what will be happening? So here, what we are doing is, each day we are interviewing for hiring assistant problem. Each day we are interviewing one student, and our objective is to see that whether a candidate is hired or not. Okay. So it is similar to this individual coin flip where we see whether head is coming up or not. Okay. So the same thing is happening, right? Only the case we will be seeing that probability will be changing. Other than this, it is absolutely remaining same. Okay. I can think of that n number of interviews are going on. Okay. N number of interviews are going on, and the sample space could be, okay, this say 4 interviews are there. So this higher, 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 all hiring. Or the sample space could be, so if I am taking the random variable as a big random variable, that means all in n coin flips or all in interviews coming together. Okay. Then it will be higher, 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 not higher. Okay. N. So like that way we can have this sample space, and then we can define the random variable, and then how many hiring will be there. We can take the values of X, and then with the help of that expectation formula, we can find out the expectation of X. That is one way. Okay. And the other way is we have to decompose N interviews into simpler one. We are concentrating on the ith interview. Okay. And it is exactly becoming a single coin flip experiment. ith interview only. Right. And we are looking for that ith guy who is getting interviewed right now hired. Okay. So that means hired or not hired. So this is exactly, so we can define this for a particular ith interview. Okay, we can define one indicator random variable xi, and that indicator random variable is associated with this event A, and this A, in this case, A is ith candidate higher. ith candidate higher. Okay. So this event A, this is exactly the same line of treatment going on. If I know that coin flip experiment exactly, I mean, if we know it philosophically what is going on in coin flip experiment, that we can channelize into our this algorithmic problem as well. Okay, so that is the main point here we want to have, right? So this the coin flip experiment or the rolling a die experiment, it is so general. That's why in every probability class it is taught. But until now, we are not knowing where and how exactly that will be applied in our computer science field. Okay. We are trying to understand when and where this coin flip experiment or rolling a die experiment, we can apply that knowledge into our computer science field. Okay. So the mathematics, almost everything is done this in mathematics. Okay, we are hiring the knowledge of mathematics, and we are in an ad hoc manner we are applying that knowledge in computer science, we are applying knowledge in physics, we are applying knowledge in chemistry, economics, and whatever. Okay, so that's why mathematics is called the queen of sciences. It's so pervasive. Every time we are having trouble, we are doing all these things without a single experiment. We are having this electromagnetism discussed, okay, with the help of mathematics. And Einstein sitting in a room with the mathematics, he is solving relativity. So physics is becoming nothing but the mathematics. So this is the thing. This xi, we are having this indicator random variable associated with this event A, and A is, so this xi is for each interview case, what is going to happen. And we are defining indicator random variable for this associated with this event A, and that event I am writing that ith candidate hired. Okay. So that we can define one if hired, 0 otherwise. Okay. Right. And we are having this big random variable x. So that is counting that whether the first interview hired a candidate, the second interview hired a candidate, and so on up to xn. Okay, so that means the same thing, same treatment we are having. That okay, the same treatment for this coin flip experiment. Up till this, everything is same. Only this event A is changing. In the coin flip experiment, that event A was whether that particular coin flip becoming head. And for this hiring assistant problem, that ith interview, whether ith candidate is higher. Okay. So now what we got to do is we have to somehow now we are having this thing. We are having this thing, then we are taking expectation both side. We are having expectation both side, and then by linearity of expectation, that expectation to be inside. Okay. So that treatment will be remaining same time after time. Okay. And now this expectation of xi, this is what? This expectation of xi. What is xi? This is related to huh? Huh. So this is related to the experiment that ith candidate is higher. That means that particular ith interview I am looking for. Okay. And what is the expectation that on that interview? On that interview, what is the expectation? How many guys will be on expectation that will be hired? Okay. And this expectation of xi, this is related to this indicator random variable. So then we know that by lemma 1 it will be nothing but that probability of event A happening. What is A? A is the candidate I is hired, or ith candidate is hired. Okay. Now we have to find out for our coin flip experiment. We found that okay, this probability A, that means the event A is happening, that is half. But for this hiring assistant case, what this probability is. Okay. So now for this, you have to remember that when this say CDC cell or this NIT Durgapur is giving Google this list, okay, then what Google is doing, Google is randomizing the list. Okay. Right. And in that order, whatever randomized after randomization, what is the list order? On that order, we are interviewing each and every candidate. Okay. So now this first thing we have to notice that okay, we have randomized the list. Okay. Now so first I candidates. So whatever randomization we have got says this is the total list. So this guy is there, then this guy, then this guy, then this guy. This is the randomized list we have got. Now at any particular point, so this is the ith point, ith interview is getting processed. Ith interview. So if this list is randomized, then up till this point, so if I take any segment of the list, that is also randomized. There is a proof for this. So whenever I am taking this ith candidate into consideration, I know that this segment of the list, okay, this segment of the list I have seen so far. So far I haven't seen all these guys. These guys will be appearing afterwards. But I have seen, including this I, that means I number of candidates. I have seen this guy is interviewed already, this guy is interviewed already, this guy is interviewed already, and this guy is going to be interviewed. Okay, so including this guy, how many guys I have seen already? So this is I number of guys I have seen already. And that list is already randomized. So whether this ith guy will be hired or not, that is equally likely because this is the list is randomized. So anybody can be selected. Okay. So this ith guy, whether he or she will be selected, is the probability of this is 1 by I, equally likely case. So this is I is the number of candidates we have seen so far. Okay. right? If I am having n number of candidates, here, or say n number of balls we are having in a bucket, and I am picking randomly one of the balls. Say, then what will be the probability? So n number of balls we are having. What is the probability that this guy will be selected? It is 1 by n, equally likely case. Okay. What is the probability that this guy will be selected? It's 1 by n. Okay. Right. Anybody in this, because we are selecting the balls randomly. Okay. So here also, this whether ith candidate will be selected or not, I have seen so far this including this I number of candidates. Okay. So out of this, whether this guy will be selected, its probability is 1 by I. Okay. Equally likely case. So here n equal to I so far. So this expectation of xi, now expectation of xi means probability that candidate I is higher. So this will be 1 by I. Okay. So now this thing will be putting here. So this expectation of x, the probability of that event A is happening. So that means by our lemma 1, we have got this, and then probability of A we have calculated, this is 1 by I. Okay. Now this is, you see, I have written one thing, Hn equal to this k equals to 1 to n 1 by k. Okay. So this is a very important series. This is called harmonic series. Okay. So the series is becoming, if k equals to 1, it is 1, plus k equals to 2, it is becoming half, plus like this way 1 by n. Okay. So this series, what will be the summation of this series? And it is less equal to log n plus 1. Okay. So this we can prove. There is a proof in CLRS appendix. You should be going through it. If you are not getting this, then I can help you. Okay. So the idea of that series is that, okay, we can decompose, say, this first group will be 1, and then 1/2, 1/3, and something else will be in another group, and then there will be another group. Okay. So all these groups will be less equal to 1. We have to see. So this 1 is itself less equal to 1. So this group will be resulting less equal to 1. This group will be resulting less equal to 1. Okay, and we'll be seeing that we can have at most log n number of groups. So log n number of groups will be contributing, each contributing 1. So we'll be having almost this result. So there is a very elegant proof is given in CLRS appendix. You just go through this, and the philosophy is this. Okay. So this result say Hn equal to this is harmonic series result we will be applying right now. So this is, you see, expectation of x is I equals to 1 to n 1 by I. If I place it k equals to 1 to n 1 by k. So that is exactly this expectation of x is this, that means it is the harmonic series. So this is Hn. And this I have got that this is less equal to log n plus 1. Okay. Or we can write, say, this is order of log n, but this, whenever I am writing order of log n, maybe if I think of original function, then it might be, we might be thinking it is 2 times log n, something like that. Okay. C times, it is less equal to C times log n. We can think of 4 times log n, but that is still not a good result. Okay. So at times, instead of order of log n, if I am writing less than equal to log n plus 1, it is the better one. Okay, better interpretation means 4 times log n might be if the log n is say 4, then 4 times log n it is 16. Okay. But if I am writing log n plus 1, then it will be 4 plus 1, 5. So I am seeing that the number of hirings for n number of interviews, okay, n number of interviews in that case is becoming 5. Okay. If say n equals to 16, right? So this is the result we are looking for. We are looking for that, okay, this expected number of hirings will be order of log n. Order of log n, and we have proved this. So this is proved. Okay. So this hiring assistant problem is over. Now in the next class we'll be having this quick sort. Okay. So we'll be having quick sort in the next class. Randomized quick sort. Any question?